Okay, so this is where we started last time. So I'll open up the motor model which we created last time, and yeah, this is what I shared with you on the Teams group. This is the motor model, and these are the parameters which we set. And for the reference, I've also shared this link so that you can actually see how do we easily make a transfer function using different equations, right? So so yeah, so last time we made this motor plant, DC motor plant and model, and uh, so we had certain equations, and then we try to make uh, make a transfer function through it, or maybe we actually divided the equations into different parts, and then we tried to assemble it using this controls flowchart in the Simulink, and then we actually compiled all this model within this box, and we then applied a voltage, and we got angular velocity out. So if I just run it, so currently my voltage is set to 25 volts, and the step time I'll keep it 1. This is just to revise what we did last time, right? So again I'll run it, and oh, okay, I'm not sure what is wrong. Okay, yeah, I actually zoomed in, so that is why. So this is what we got. So if we want the output angular velocity to be 2.5 radians per second, we had to apply 25 volts of uh, of signal, and then actually last time we saw, like, we also added some controllers, I guess a proportional controller. But before we start this time, I guess I'll just briefly touch what how a typical control system looks like, and and then we will proceed to the PID, more industry accepted controller called PID controller, right? So in a typical control system, we have a reference signal actually. So a reference signal is one which we want to track actually. So if I want my angular velocity to be, say, one radian per second, I'll give my reference signal as 1 radian per second to the control system, and then I expect the system to reach that 1 radian per second goal, right? So that is what we call as trajectory tracking or reference tracking, basically. So then we have a plant. So in our case, the plant is the motor, DC motor actually, and that is the thing which we want to control actually. So I'll name it plant, which in our case is DC motor, right? And then we have some output out of this DC motor, right? And but the problem is, if you see last time what we did was just apply even, yeah, if you see in this case, we are just applying a voltage directly to the motor, right? And then if we want to actually get some output, we'll have to calculate the voltage, right? So so basically the input to this is a voltage signal, is a voltage which we are applying to the DC motor. And for converting that, uh, this reference signal to a voltage, actually we'll have to use a controller block basically. And this will basically convert my angular velocity to voltage, and give this voltage to the, so voltage will be provided by the battery, but it will regulate the voltage which we have to apply to the plant. And uh, and this is how open loop system looks like. So, and in an open loop system we, yeah, in a open loop system we actually have just a reference signal, then a controller, and this controller actually this controller actually provides the information of the, it converts the reference signal to voltage signal according to the reference. And but the problem is we don't have any feedback for this. So if my reference, if my plant model say changes by some amount, I want my controller to be robust enough so that I still can track my trajectory reference signal, right? So for that reason we, what we generally do is we apply a feedback loop actually. So so feedback loop actually looks something like this. This is my uh, final output. So in our case this is the omega output, right? And this is the reference, omega reference, right? And then this is basically a feedback loop which we want to give it to our system so that we can maybe make the control of the system much more robust, and so that we get some kind of feedback back from the output on. So suppose if I want my omega to rotate by, if I want my angular velocity to be 1 radian per second, and I'm getting uh, output of zero point 0.1 radians, so there is no way to find out uh, if my output actually is in line with the reference signal, right? So we basically use some kind of feedback, and generally we use negative feedback because negative feedback gives us kind of an error between the output and the reference, right? So this is how we actually sum the signals, the way we saw last time, right? We added a few signals, we subtracted them, and all those operations actually. So this signal is kind of a negative. uh, we just subtract it from the reference, so we get something like an error term here. Well, e, right? Then this, okay, this should be error. I just by mistake wrote it E. So this error goes inside this controller, and then this controller accordingly adjusts the voltage which is given to the plant, and then the plant basically modifies my output, and then there will be some improvement in the output maybe, and this output is again a feedback of this output is again given to the reference, then again a new error is calculated, and this is how this closed loop system actually works. There's also a sensor model which is generally kept here. So a sensor actually takes the value from the actual quantity and gives us the feedback uh, of the signal, output signal. to the control system. So if in my case this plant is right now a motor, right? So we generally attach a sensor called encoder to the motors, right? So has anyone seen any encoder or DC motor on a DC motor in the class? Or like, does anyone have an idea why we use a sensor model here? Any guesses? Random guesses? Anyone? Okay, so I guess the class does not want to interact much, but the sensor model, we create this sensor model just so that since my output might be in radians, the encoder takes this calculate tries to calculate the signal which is in the form of voltage. So the output of this sensor is in the form of voltage, but we want I want my output to be in the form of reference omega only, radians per second only. So this model actually converts my uh, voltage into uh, radians per second and gives it to the controller back. So that is why we create this sensor model. But when we go about in Simulink, we just directly connect this output to my negative side of the sum. And also there are some inconsistencies in the sensors sometime. So suppose my output is say one radians per second, but there is some kind of an offset of zero point 0.1 radians per second in the sensor. It might measure zero point 0.9 radians per second, but currently when we start building the controller, we start very simple and then we start modifying different elements of the sensor, different elements of the environment actually. So there might be some noises in the plant model or in the sensor model, right? So we try to later on add these things to the controller, add these things to the model, and then we modify the controller accordingly. Okay, so in the Simulink, we'll just start with changing this voltage to a reference signal, omega reference, right? And I'll also delete this. So this will be connected to the. I'll also add a sum. So if you remember, we added a sum block last time, right? Which which actually helps us to take a sum or subtract two signals based on the signs which we had. So we have this sum block which will take a negative feedback of my output signal. This is my plant. So we'll just try to make this model as it is, and then we add a simple gain block probably. So I remember last time I also added this gain block just to give some idea of how a control system looks like. And so this time I actually wanted to give some basics uh, prior to our starting, maybe, so that everyone knows how a basic control system looks like. Okay, so if you have any doubts, please don't hesitate to ask me. And it is very important for you guys to actually understand these things so that you can actually proceed further. So a basic controller which directly comes to our mind is a proportional controller. So currently I just keep the proportional gain to one only, and then I'll see what my output is. Okay, I actually forgot to change the reference signal. So Now I want my reference to be say 2 radians per second, right? And then we run this system again. Uh, Probably scale it. Yeah, so if you see that my output is not able to catch up with the reference signal which I'm giving, so I'll probably increase this to say 10 times, okay, and then apply it, okay, and then again run the simulation. So if you see, when I increase the gain to 10, my signal actually jumped. The output signal of my angular velocity actually increased to one radian per second, but I want it to be 2 radians per second. So probably I'll increase it to 20, and then again run this. So if you see, there was just a slight increase in the signal. So then we actually increase it to a larger value, and then we see that there is an overshoot. So an overshoot is the quantity by which my signal increases in the transient phase above the reference signal actually. So if you see the value to which it shoots above my reference signal is called an overshoot, okay. So in this case, when I increase my gain too much, the overshoot also increase. Plus if you see, there is some kind of an offset, right? uh I guess the offset is around zero point 0.2 or something. So if I see, currently the value at zero point 0.2 is 1.818, right? So we have some offset, steady state offset. So we also want to actually decrease this offset, right? So do you have any suggestions on how I can decrease this offset? Anyone? So yeah, it will be good if you will be able to learn it in a much better way if you start interacting, so that we can have a good discussion, and we can discuss on on different possibilities of developing a controller actually. So anyone, any idea? Okay, so probably one way is to just we keep on increasing the proportional gain. But the problem is, if we start increasing, so if I'll show you again, I'll increase the gain to 200 and run it again. So if you see that the overshoot actually increased, right? So earlier it was around 2.2 or something. Now it increased to something like a 2.6. So there's an overshoot of 20% actually, right? And plus there is a constant steady state error as well. So one way is, can we somehow take this error, right? A steady state error, and then try to give this as a negative feedback again to my plant, so that it tries to minimize this area, the area between the reference and the final output. So what comes to our mind when we say area? It is an integral, right? So we'll add an integration block as well to my controller, and so I'll first add an integrator. I'll double tap again and then add an integrator, and then some gain block again, so that I can train the like I can actually vary the constant which is attached to the integrator. Okay, I'll have to add one more summation block. So again a double tap, sum, and three plus signs, two plus signs. Okay. And yeah, I just added an integrator. So the integrator will actually add the area term as well. So if you see there is an offset, right? So if I can also add my area, so I can add a I can if I actually take area into account, it will try to minimize this area, right? We should try to decrease this area, because when we start to increase the proportional gain, uh, there are two problems. The steady state error is not decreasing so much, but the overshoot is increasing too much. So the overshoot actually, we want this overshoot to be within some limits, so that minimize this overshoot, so that my my plant does not go too much beyond my reference signal, right? It stays within some limit. So I don't want my overshoot to be too much, and at the same time I want to decrease this area. So let's now see what happens if we add this integrator. Okay, there isn't much difference, but I'll try to increase the gain which is associated with this. Hit OK, apply, run. Yeah, the value actually decreased by some amount. Probably I'll have to increase this more. So actually you have to put in values, different values, and then actually you have to see. Maybe I'll decrease the gain, proportional gain, and see again. Right, yeah, now you can see that the show overshoot actually decreased because I decreased my gain, right? And then the steady state error is also going to almost zero, right? So yeah, if you can see that this integrator signal is actually helping us in decreasing uh, the steady state error which we had earlier, right? But still there is a problem of overshoot, and along with overshoot, uh, we also have certain uh, variations in this. So if you see that the signal first goes up, then again goes down, then up, then down. So we want to reduce the uh, this variation which we are seeing in the output signal, right? So one way is we decrease this gain and try to increase this, right? So if I decrease it further, apply, and then again, we'll see that the overshoot has decreased by some more amount, plus uh, plus my uh, the variation is somewhat decreased. But still also there's one more quantity which I forgot to tell you. There's a rise time which I consider. So rise time is the amount of time it takes to touch my reference signal. So I also want to decrease this rise time at the same time. So these are few factors which we consider when we assess the quality of a reference of a signal, actually, of an output signal. So to decrease the variation element in this, we add a differential element, actually. So I add a derivative, is a continuous derivative term. I'll add this to the and add one more plus sign in this probably, and apply. Okay, and again gain block to control the gain of the derivative block. Right, I'll name these blocks. This is what we call kp, kd, sorry, ki. This is because we are multiplying this with the integrator, and this one is kd. And then I'll just keep it one right now and see what is there any difference. So if you see, it tried to actually decrease some variation element in this, right? So I'll increase the kd block again and hit run. So if you see, the variation actually is decreasing somewhat, right? So if you want to see it in a magnified way, you can see that the variation has decreased a lot, right? uh but the problem is, earlier we had uh this settling time which was like 3 seconds, but now this time has actually uh increased by some more amount, but the variation has actually decreased. And then if I increase the gains of the kd block again, so yeah, you have to actually change a few parameters here and there, and uh, you have to get a good signal, actually, which has a very low overshoot, but we also want a quick rise time and a quick settling time as well, plus a signal with very less variations, right? So probably will also there is a so probably you'll have to actually sit and tune the gains so that you get a very good kind of uh, an output signal, probably that has a uh, very low rising time, very low overshoot, as well as a quick settling time as well, right? So plus you'll have to actually make this controller again and again. But luckily in Simulink we have a we already have a block for PID. I'll shift this thing to the top probably, or anyways I'll delete maybe this. and search for a PID controller. So if you can see, this PID controller is just it is everything in this box again, and it looks bit less clumsy actually, and more like a classical control setup right now. Okay, so my so if you see, if I click this, double click this PID controller, we'll see that there is a proportional gain which I have to put, an integral gain and a derivative gain, plus we also have a filter here, right? So if we see in a differential, when we add a differential term to the a derivative term to the controller, there might be a lot of variations actually, a sharp change in slopes sometimes, right? So if there is a sharp change in slopes, this term will shoot actually. So if the frequency is very high, this derivative term will shoot very high, and we do, so we want to actually avoid very high frequency signals, so we put a filter actually, a first order filter. And a first order filter basically removes all the higher frequency signals and just gives me the output as low frequency variations. So all we just want right now is to decrease the low frequency variations, so that my my derivative term is in control, and plus I am able to actually get benefit of this derivative term again, right? So probably I'll just run this and see that when I put values of 10 and 10, I was able to get a response of this sort. There is no overshoot, but the rising time and settling time are too long actually. So I'll probably add some kind of derivative term. So this gives me a better signal, right? So the rising and the settling time are a bit faster right now. So that is, so your job will be to actually uh in the actual world, your job will be to actually train, like tune these values, right? So I'll probably wait for some time for you guys to actually tune these parameters right now, and give me if and give me your value, so that we can see what all values we have, what all tuned values we have, right? So you guys can probably try adding this proportional block. So do you guys face any problem while adding like making the system? Just adding you just have to add a proportional block here and add this summation block, so that I can take a negative feedback and give it to the controller, which will give me a voltage output actually.
Yeah, Manan.
Yes, sir.
Yeah, let's go back to the controller block.
Yes, sir.
So in the meanwhile, the students, as they tried this at their own. So if you keep the derivative term 0,
Yeah.
and let's have an integral of 50.
Okay. Okay.
Let's see what the output looks like.
Sorry, sir.
I said, let's see what the output looks like.
Okay.
Okay, so we
So
now
yeah.
have some overshoot, but the rise time and the setting time have improved.
Yeah, they have actually
So
decreased.
Yeah. So if we can tolerate a little bit of overshoot, then this PD or other PI controller works well, isn't it?
Yes, yes, sir.
Yeah. So see now what we're actually doing is that we are uh, tuning the controller manually in a way. So there is a systematic way of doing or tuning the uh, controller parameters. Yeah, are you listening to me?
Yeah. Yes, yes, sir. We are able to listen you. So
Yeah.
yeah, so if you
So
go deep into the tuning of these parameters, there are some systematic ways which
yeah.
you might
Okay.
see when you go deeper in the PID controllers. So
Yeah.
maybe using
So
Nyquist plots, or there is a method called Ziegler-Nichols ZN methods.
yeah,
So you
Ziegler-Nichols method is something that see. My sort of apprehension is that some of the students are not conversant with control systems. Okay.
okay, sir.
So yeah. So, but then again, this is not something which is very difficult to learn. So my suggestion to the students would be to just try to see the power that Simulink offers. Okay, by just choosing the parameters arbitrarily, by increasing the proportion or decreasing it, or by increasing or decreasing the other two proportional, rather the gains of the other two controllers, you can keep on trying till you get an output that you actually desire. So that's where the power of Simulink lies. So are students are you working on your systems simultaneously, or you're just looking at the presentation? Anyway, so Manan, please continue.
Okay, sir.
Yeah,
So yeah, actually, if you are just looking at it right now, I'll encourage you to go after this tutorial, and since we are recording this session, you can actually sit down and make this system. I've actually sent this motor plant model. So all you just have to do is add a PID controller block, right? And then you have to actually get a hang of this of each component, like a proportional, integral, a derivative term, right? You just maybe keep one thing as zero, and other non-zero values, right? So if I want to have a PD controller, so probably I'll add this, and then you can actually uh, run and then see that like what actually is happening, right? So this in this way you will be able to appreciate why a PID controller, which looks very simple, like if you see there are a lot of very complex controllers which we are working around, but still if you see PID controllers are used by around 70 to 80%, uh, like they constitute of 70 to 80% of industrial controllers actually.
yeah,
so
yeah,
so the
Manan. Sorry to interrupt.
Yes, sir.
Let's keep the filter coefficient to zero.
Yeah, sure, sir.
Let's see what happens.
So basically, when we keep this filter coefficient zero, this term will actually go to zero.
Go on.
Yeah.
Let's simulate.
Okay. So basically, it will become a proportional controller again. So
So
yeah, if you
if you
see
keep it
that we
one,
don't have an integral right now, so I'll just put an integral as well.
so let's have one as the this filter coefficient. I think the performance should now improve.
Yeah. So the performance actually is improving. The overshoot is not that much, but
Yeah,
the settling time is pushed forward, but there are no variations actually. So if you see just a
So
single
if I
overshoot happening.
yeah, sorry to
Yeah, yeah, yeah,
I
sir.
want the session to be more interactive so that the students, let's now increase the proportional gain.
We
Let's say to
increase it,
100.
sir. Okay.
Yeah, let's see what happens. So integral, we have we I want the integral to be 0.
Okay,
No,
integral
no,
to so
yeah,
probably
0.
there
Yeah.
is one more thing which you can add. So there is something called a dashboard scope.
Okay.
So if you add this dashboard scope, you can actually see the values real time here itself,
Hmm.
the responses. So all you just have to do is connect different. Yeah, I'll add this, and as well as I'll add another signal, probably this one, right? And then I can run. Yeah, so if you can see, you can actually get the values here, the graph here itself. So it is much more
Yeah.
easier for you to actually play around and then see the graphs alongside actually. So you don't have to go to this scope and see measure things again and like see the graphs again and again. But if you want to measure the signals, right, then probably this scope is better. But if you just want to see the shapes of graphs and just to get a fair bit of idea of how a graph looks like, you can actually use a dashboard scope actually, right? So yeah, again you can actually, since we just want to see the shapes of the graphs right now, we will use this scope probably. So yeah, sir,
So
please.
let's have the integral control 0.
Okay.
Let's see what the graph looks like.
Yeah, so when we decrease it to zero, there is an offset actually. So there is a steady state error, which
So oscillations. So let's try to reduce the proportional controller as control as well.
yeah, yes, sir.
Keep it 50.
So yeah,
So
this
the offset.
actually, so probably we can also increase the filter coefficient as well, or add some kind of integral. So yeah, if you see, as we added an integral, this is a very good example. If you see, there was like where the integral is actually very evidently working exact. So there was a constant steady state error, right? When we added uh, an integral term, the integral is actually forcing it to reduce the area under the curve actually. The area actually not under the curve, over the curve and below the reference actually. So this area, basically the area between the green curve and the pink curve. So so yeah, if you see that so yeah, actually now if we are done with playing around with different gains, there's just there is a simple way to actually tune these parameters automatically. So there is a button called tune here. So if you just click on tune button here, what it will do is it will directly take different uh, it will directly train different PID parameters actually for you, and you can actually program what response time you need, what transient behavior you need, right? You need very aggressive kind of transient behavior or a robust kind of behavior. So by robust, we mean low overshoot. But if I'm okay with a very high overshoot, uh, fairly bit high overshoot, we can use this as well, right? So suppose you're working on some project actually, uh, say making a line following bot or something, right? You can actually make a model and then actually basically tune the parameters. So your job of tuning the parameters now is basically done itself automatically by Simulink. So you can see this is the response which we have currently. So if I just shift these. So this is the behavior which we have currently. You can see here the green one is this dotted line, and this solid line is actually the tuned response. And I can actually uh, make this I can actually program this based on my requirements, right? So if I want my response time to be faster, I can increase it. I can decrease the response time. Plus, if I want my uh, response to be much more robust, right? I can also decrease it. So if I'm actually making a controller, I want these two things to be good, right? So, but the thing is, I think it is also increasing the settling time. If I make it both response time much more faster as well as robust, right? So we'll have to actually
So
stack. Yeah, yes, sir.
yeah, if you want to look at the gains for the tuned response, where are they in the menu?
So if I just update the block, right, sir?
Okay.
Just yeah. If I just update the block, if you can actually see
And
that
okay, yes. Okay. Okay.
they are
Okay.
they are directly updated in this itself. So if I again
Okay.
hit
Fine. Good. Yeah. Got
and
it.
run it, you'll see that this response is almost like the settling time is also quite less actually. So
Yeah.
I
Yeah.
guess it is
So
around yeah.
yeah, it's a reasonably good response. I we expect the overshoot to take place sort of a little bit, and then uh, the other properties like the settling time and the rise time are pretty. In fact, the rise time is outstanding, which I believe that when we actually try to implement the things in hardware, will be very difficult to achieve. But insofar as the simulation is concerned, the rise time is excellent. Okay, apart from the little bit of overshoot, okay, the steady state response is quite good. So this is for the students if you are able to appreciate this problem. Okay, by choosing the parameters. Now Simulink has actually chosen the parameters for us, and we're getting a fairly good response. So any
Yeah.
question, any questions from any students to Manan or maybe to me? I I'm not sure how many people, how many out of you have taught control, but I think we did discuss PID controllers, and there is a complete theory which probably will help you to appreciate what we essentially do when we use a PID controller. Okay, Manan, please go ahead.
Yeah, sure, sir. So once we have this PID control, right, we can actually maybe I'll open the scope itself. So we can actually zoom in and see what all different like what are different values that we have. And if you closely see it, uh and I choose my cursors to place here. I'm sorry. Can If you want to see the response very closely, can actually see that like by the time, say suppose what 1.8834. So that is since we actually started the block the step response at 1 second, so it is actually settling it within 0.834 seconds actually, which is quite good actually if you see. And if you even zoom in and if you want to see the steady state errors, right, you can actually see that uh, these are almost yeah, these are actually almost able to track the reference signal that I'm giving in a very good way, right? So if you say I want to change my uh, if I want to add different signals, so suppose I, instead of just a block response, right, I want to have a double block kind of thing. So probably I'll just add another step response, right, and add it directly to this, so that, and basically instead of instead of starting at 1, I'll probably start it at 3, right, and the final value is maybe 3, and then I hit apply. And so I have to add a some block. Yeah, so if I run this, you can see that the reference signal is this first. Oh, I actually added 3. Yeah. So my final value is also 3. The total will be 5 radians per second, which the step will be taken at 3 seconds actually. So if my signal looks something like this, so suppose if I have a controller in my hand, a remote controller, right? I at 1 second I wanted to rotate at 2 radians per second, but at 3 at the third second I want to actually increase the velocity to say 5 radians per second, right? So you can see that since my so just to make you appreciate why this controller is quite good, this settles in at 8 seconds, right? 0.8 seconds, right? So my so I can actually uh, change my inputs from the controller at a much more faster pace. So if you see, if my controller took say 2 seconds or 3 seconds to settle in, I would not be able to get a good response in that way. So probably I'll keep on increasing my uh, so there is a feedback loop which goes in my mind as well, right? So I can see that the robot is not going at my desired pace, so I'll increase the reference signal further. But then when I increase the signal further, there is a lag in catching up of that signal, right? So suppose if my signal settles at in say 3 seconds, but at the second itself, like in the at time t equals to 3, I change my reference signal to 5 radians per second. Then it will take another 3 seconds to settle to this velocity actually. But it will go far beyond my 2 radians per second, right? So having a low response time, quick response time actually helps me to get track my velocities very in a very good way actually. So so that is why actually we want a good response time, which looks which should have a low overshoot as well as a quick response time actually. So so yeah, actually this is what we actually which what I actually plan to tell you this time. And I was actually expecting some students to come up with different models so that we can also try those, like the one you told last time, sir. Some spring damper model or something. So we could have actually played around and actually analyzed how different systems actually work, and how we can actually tune the parameters, right? So like, since like, has any one of you prepared any other models or any other things that you feel that you can have? So if you have, probably you can actually share your screen, and so that others can also know how you actually made the model, and probably add this proportional PID controller to it, and we can see what we like, how we can tune it. Okay, so if not, I'll actually proceed further. So yeah, actually, if I see uh my scope, right, the voltage which is going inside my motor, I'm not measuring that right now, right? So what will happen if my delete this. So what will happen if I see my voltage output, because my battery can actually provide me only a limited amount of values, right? I'll probably close this and see how my response looks like, right? So if you can see, there are two spikes here at time t equals to 1 and time t equals to 3. So also add a legend actually. So this will help you to see what each color signifies. So if you can see that these two yellow colored spikes, which signifies my output of the PID controller, you can see that this there are two spikes, right, in uh, the voltage side, and that too in 10 raised to power 4, right? So this is something like 11 into 10 raised to power 4, 16 or 7, 16.5 something into 10 raised to power 4, which is a very large, like this is around 160 kilovolts actually. So which is not actually very practical just to drive a motor, right? So we cannot afford to have such a large voltage, and that too for just very small amount of time, to just drive a motor at 2 radians or 5 radians per second, right? So I want the output of this to be capped at certain practical voltage values, right? I'll for now actually I'll comment out this thing. Yeah. So we cannot afford to have such a large voltage. So probably what we'll do is put some kind of output saturation, right? So I can limit my output. So practical value may be 12 volts and negative 12 volts. So negative 12 volt can be like a range if I just place my battery in the reverse direction, right? And let's now see the output. Yeah, it is much more practical now, I guess. So if you see my voltage values, they are constantly at 12 volts, and my output response is not very good, right? So I'll have to train the PID values again. So yeah, also
Yeah.
if you see
Oh,
that,
oh, just a second, Madan.
yes,
Yeah. Apart from the offset, the DC offset that we have, or the steady state error, the response is reasonable. Okay.
yes sir, the
So
response.
what this will work perfectly if we take the steady state error into account. For example, if you want to run the motor at 2 RPM, or radians per second, okay, we know that it is going to the output is going to drop by a little bit. So can't we compensate by just increasing the input signal by, let's say, another uh, some amount, so that finally we get the desired RPM? So that way, this can work that way as well. Am I right?
Yeah. Yes, sir. So also if we actually tune my parameters, so actually I put my control parameters very like at very in that way very idealistic, right? So I put my response. I want my response to be very quicker as well as less overshoot, right? So probably I'll do is I'll tune these parameters again with my output saturation and see how my response changes now. So how an ideal response now looks. So currently uh, like my block response looks something like this, and attuned, okay, so it does not actually look like this. It looks something like this, and probably if I see, yeah, so the block response actually does not look something like this. So probably we'll have to tune the parameters now again with hand. So as far as I remember, yeah. So in this, so now in this case, actually, PID tuner actually gives us tunes the parameters, just keeping in mind the it does not take into account the saturation actually. But now let's go with a less aggressive kind of tuning. So I'll update the block parameters and see how my output actually looks like. if I run this again, so probably I should have seen the values first. Currently it is around 1.2. So we'll have to again make it a bit less aggressive in that way. So maybe I can try to have a bigger overshoot and slower my response time, so that I can now have a better okay, yeah. So now, as if you can see that I don't need 12 volts from first second itself. It is going up, so we are actually on the improving side. So if I actually reduce this and this, so make it a bit slower again, and then see. So yeah, actually, although the response time is not changing much, but uh, like using, since we are just using it at 12 volts, and the response is a bit slower right now. So the 12 volts cap is touching at a bit at a later end actually. So actually you can see that this value cannot be achieved with this 12 volts kind of signal, 12 volts kind of voltage, right? So probably your job will be to uh, is to tune the parameter, so that we, or maybe probably what you guys can do is check for different reference signals, right? So suppose, say, uh, one radian per second, and see if it is able to achieve that signal or not. So probably I'll just change this to 1 radian per second. I hope that will be able to get that kind of response achieved. Yeah. So if you see, we are able to achieve this because it is well within the range of 10 volts is the saturation voltage. And since we 10 volts is the steady state voltage, and 12 volts is the saturation voltage. So since 10 volts is well within 12 volts, we are able to achieve this response within a reasonable amount of time. And we are actually able to achieve this with 2 radians per second. We were not able to achieve this. So now I'll just go on making it a bit like making my response a bit better, and again run this. So yeah, making it much more aggressive, like making it much more idealistic. We were at first we touched this saturation point, but then eventually we settled at 10 volts actually. So so my guess is if I keep my output as if I want my output to be 1 radian per second, probably I'll have to either supply so I'll have to so I can achieve that. But if I want to achieve a higher velocity, say 2 radians per second, I'll have to either increase my voltage somehow, or probably maybe you can try and tune the parameters in a way so that it touches it. But I'm not sure that it is going to touch it. So either you have to change the motor itself, because the motor parameters, they certainly don't seem to uh, support 2 radians per second with 12 volts of saturation voltage, right? So either you'll have to change these things a bit, or change the battery or the motor to achieve 2 radians per second actually. So you can actually play with these values, either the motor values here, right? Or you can play with the saturation, or maybe probably see what is the uh yeah, what is the maximum angular velocity that we can achieve with this kind of uh, with this setup actually. So I think this is fairly complex as of now, so you can actually go ahead and tune your parameters so that you can actually make a real world robot, and then apply the knowledge of PID to your robots, right? And uh, and well within the limits, right? So this Simulink actually gives you all the tools that you require to basically make a controller for your actual real world robots, right? So there's, I guess there's one more plugin for ROS. So ROS is basically robot operating system. So if I want to control uh, if I want to connect a hardware to my MATLAB controller, I can actually do that using ROS. So like these all plugins are available in MATLAB actually. So all you just need to, if you want to become a good robotics engineer, you can actually you have a lot of resources to be explored in MATLAB and Simulink actually. So you can go
Yeah,
around and
a quick question.
yes, sir.
Yeah, this ROS, does it work on Windows operating system, or we have to have a Linux machine?
So actually, sir, with MATLAB, I guess we can use with the plugin for MATLAB, we can actually use in Windows or whatever system we like. But if I want to use
Ha-
ROS,
have you actually used ROS?
yeah, sir. So actually, we are using ROS in our lab actually, but we
Absolutely.
don't use
Okay, so
MATLAB actually. So
yeah, so I am actually interested in sort of using ROS. So
yes,
if you could provide instructions as to how to download it and configure it, that would be a
yes.
good exercise for the students. We can download ROS, and then we can do some robotic exercises using ROS. So once we have ROS installed, okay, so that will directly control the hardware.
No, sir. Actually, you have to make a controller. So ROS is just a just it helps us to make a connection between my controller, my hardware, and all the other things. So if I have a
No,
controller, a remote controller, I'll have
mhm,
to make different nodes, which will signify the output and the inputs of different things. So I have a set of sensors, set of motors, set of controllers, right?
mhm.
So it just helps me to have a dense kind of network for like helps me manage these networks actually in a pretty
So
good manner.
if I understand, ROS stands for a robotic operating system.
Yes, sir.
So
But
is
actually,
it
it's
an
not
operating?
an operating system actually.
Yeah. So which operating system does it work on?
uh, Generally, if I just want to use ROS directly, Linux is a preferred uh,
Platform.
actually platform. Yeah,
Yeah.
OS.
And then
So
if you don't suppose if you don't want to go to Linux and you want to keep on using Windows and Simulink, then you can still do that.
yeah, actually using MATLAB, there is a plugin for ROS actually.
And which we
So
have to download. Huh?
yes, sir. Yes, sir.
Okay.
So
Okay. Okay.
So
Okay. Good.
actually, I haven't tried ROS with MATLAB as of now. I whatever I've used is directly I've used ROS, and now there is a second version of ROS called ROS 2. So the first version of ROS actually used C++. In the
Okay.
second version, they have given us the liberty to use Python actually.
Okay.
So Python is a bit easier. So it is more like C++ is you need to have a very good programming background for C++. For
Mhm.
Python, actually, it is a bit lenient in that way. And
Okay.
MATLAB is more lenient. So a person with less programming knowledge can actually work very well with MATLAB, then you can actually shift to Python and then C++ maybe. So
Okay.
if you don't have a good programming background, probably. So
Okay.
but yeah, if you want to like work with Python, actually the best benefit of using Python is it is free of cost. Like all the
Yeah.
libraries,
Yeah. Yeah.
most of the libraries are open sourced, and the problem with MATLAB is you'll have to pay for the license fee, which I guess is too high. And like in our lab, actually we try to keep the cost as low as possible, since we are also working with different organizations, different institutions actually, and probably we'll see if we can commercialize this in the future. So we try to use all the free resources that are available for softwares, and keep the cost as low as possible, so that we can invest more in the hardware side.
Okay. Okay. So the next example that I would probably prefer would be something where speed control of a DC motor is involved. Like, for example, if you want to move a robotic link from one position to another position with a specified speed, so
Mm.
the link should start with a certain speed and then come to rest eventually. So if we can do that in Simulink, that would be very illustrative. Here the in this example, the motor continues to run.
Yes,
Um,
yes, sir.
yeah, I want the motor to run with a prescribed speed. Okay,
Yeah, and then
and
follow a
then
particular trajectory as well.
yeah, so it's basically trajectory planning kind of a thing. But can we do it?
Yes.
Can we do it in the next session?
Yeah, yes, sir.
Okay, okay. So if does anybody have Manan, do you have anything else to sort of say, or we'll conclude the session?
Sir, we can conclude the session actually, if no more doubts are there then.
So if anybody has any questions, please ask. Okay. So as is obvious, some background in control systems is necessary when you work in robotics. Okay, and as you have seen clearly, Simulink is a very useful tool to carry out simulations. Uh, once you have the satisfactory response uh, through Simulink, then we can go to the actual hardware and try to achieve the response. So any questions from the students? Okay, so in the meanwhile, I would suggest that you do some research on ROS, okay, or robotic operating system, and it's a probably because Manan seems to be quite experienced in ROS, so we have a very good opportunity to learn about our ROS. So how to sort of in the first place we'll install it, and then how to make use of it when we actually design robots. So if there are no questions, we'll thank Manan and we'll conclude the session. So thank you, Manan. I hope we'll meet again on uh, uh, next the
Certainly.
coming Saturday, inshallah. Okay. So Rajpal was not in the class today.
Yeah, actually, sir, he has some comprehensive exam in a day or two actually. So I guess he's
Okay.
preparing for that.
Okay. Good. 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 Okay. Thank you, Manan. I think we'll conclude.
Okay, sir.
Thank you.
Okay.